Continuous is the team behind the traefik, which is a quite used reverse proxy that you maybe have heard of already. So I'm talking today about a new Go interpreter, YAEGI. So YAEGI, this is the logo that we have found. It's close to Yogi. YAEGI has been developed internally in Continuous for more than 1 year. We just announced it in July, and it's open source and accessible on GitHub. So it's it was published in last July, and in fact, right now it's still alpha level. It's not yet ready for production, but really the goal for us is to be able to use it in production in demanding environments. So what is the motivation for YAEGI, and the main motivation? In fact, if we look at Go, in fact, the Go language is very close to a dynamic language. Still, it's statically compiled. And we found that, in fact, it could be very useful to unify the high-level scripting language with the low-level compiled one. In fact, in order to be able to optimize, in fact, to optimize both the flexibility of scripting with the level of performance that you need when you run a high computation. Code demanding a higher performance. So in fact, with using Go as a scripting language, we see really it as an opportunity to improve in fact, to unify really the high-level scripting and compiling. Sorry for repeating. So what are the main use cases? Of course, we could have command line interpreters. We could have executable scripts. So with a dash bang YAEGI, in fact, at the first line. And a specific use that we are targeting with Continuous is to be able to use a Go interpreter as a plugin engine. Sorry. So let's look a bit at the goal and priorities. So we want to make the Go interpreter dynamic. Yes. It has to be embeddable in applications, so it has to be a module. It has to be simple, secure, and fast enough to be used, in fact, in applications. And it's really for production. So the design choices that we have decided were to first to prioritize performances. No, sorry, to prioritize security over performances. So, for example, we don't use the syscalls or the unsafe package by default. We still allow the application to use it, but it has to be explicitly decided by the application. Of course, a Go interpreter by itself is not very useful. One of the main benefits of the Go runtime is that it provides a very extended standard library, which is very powerful. And one of the goals of the interpreter is to be able to reuse from interpreted scripts, to reuse all the power of the Go language. So for example, we want to start Go routines, we want to use channels, we want to use concurrent code, and we want to use logs and everything. So we want to use all the packages which are provided by the standard library and beyond. And we want also to not only to be able to call binary code from the interpreter, but we want also to be able to do the reverse. We want to be able to invoke interpreted code directly from the binary, even if the binary has no knowledge, previous knowledge of what will be interpreted. So it's really a matter of making Go more dynamic. In fact, it changes, to me, it changes really the way we can use Go. It's really also, you have to see that when we use an interpreter inside an application, it's like if we are embedding the whole runtime, the standard library, but also the Go toolchain inside the application. So it's really changed the power that you are embedding, that you are providing the application. So some other features of the project. The first is that we don't have any other dependencies than the Go standard library. We just use the Go standard library and that's it. It works everywhere Go works. So it means that the interpreter has been made portable. We don't have any architecture dependent at this time, so it's kind of trade-off. We support, as the Go toolchain, we support only the two last major Go releases. Today, this is the 1.12 and the 1.13. And as I said before, in fact, by default, we don't provide access and we don't use ourselves the unsafe and syscall packages, but we provide a way to use them if it is really required by the application. So let's have a quick look at the architecture. So it's what we see here, the figure that we see here is a standard, in fact, Go application. So you recognize at the bottom the Go runtime, which is the scheduler. You have also all the features which are provided by the Go runtime: the scheduler, the garbage collector, the implementation of channels, and all the stuff. On top of it, you have the standard library, and on top of it, you have some packages like the C package 1, C package N, etc. C stands for compiled, so it means all the stuff that is pre-compiled as in any Go package. And then you have a special module, which is the YAEGI interpreter. The name is YAEGI/interp, which is the name of the package. And then you have some other custom application stuff. And in green, you have all the codes that will be interpreted within the YAEGI interpreter, and this code is in green. But it's exactly the same code, at least at source code level, it's exactly the same code as the compiled package. In fact, one of the goals was to be able to move some code from a compiled status into interpreted status or the reverse. And as I said previously, also one of the goals is to be able to use compiled symbols from the interpreted packages, and also to provide interpreted dependencies to compiled packages. And we'll see later how we do that. If we look at the API, so it's quite simple. We have only 3 main functions. The first one is new, which allows to create a new, in fact, an interpreter context. And you just provide some options to that. If you provide an empty options, it will use the standard Go path, and that's it. Then if we want to run some source code, then you have a method on the interpreter which is called i.Eval, where you provide a string, which is the source of the code that you want to execute. This source obviously is just Go code. When you run eval, it returns a single reflect value, and then even if you have some functions that may returning several values in return, in fact, we have decided that the eval just return a single resource value, a single reflect value. So reflect is coming from the reflect package, which coming from the standard library, which provides and implements a reflection. We have a third interface, in fact, third API function, which is use. Use allows the application to export some binary modules to the interpreter. It makes some compiled code visible to the interpreter. And we have provided in YAEGI an export, a special export object which contains the full standard library, so all the packages of the standard library. So when you compile YAEGI and the standard lib objects in your application, in fact, you embed the complete standard. In fact, you compile everything which is provided by the standard library. It's not on-demand inclusion of packages. You take everything at once. So it can then be provided to the interpreter. So time to move to examples. So the first, really the simplest example is to just display an hello world. So we start by importing the package itself. So this is github/continuous/YAEGI/interp. We create the interpreter, and then we invoke the eval method on it and print hello world on it. So just run it. Yeah, okay. So there is a nice feature in the GoLab. In fact, in the present tool, you can even edit code and run it again. It works. Yeah. Okay. So that's not very difficult here. And here we have everything that I displayed previously. In fact, we have the Go runtime, the standard library, we have the Go interpreter, and we have embedded in this application, in fact, the interpreter and the code in green, which is the print line. So the eval is incremental. So it means that the interpreter context that you create with new, in fact, returns an object which is persistent. This object contains the state of the interpreter at a given time, and this state can be changed during the execution. It is not just a run once and forget, it's not fire and forget. You have a persistent state that you can reuse, and you can interlace code from the application with code from the interpreter. So for example, so first I run it. Yeah. Then I will insert some code between the two things. From app. Okay, so we have the first eval, which has, in fact, made the computation and assigned a variable. Doesn't display any result, we don't see it. Then we see the print line from the application, and then we go back to the eval, and then we retrieve the content of A. So, next example. So this is still the same. We have still a main which creates an interpreter and evaluate source, but this time the source is a bit more complicated. First, we now create a complete package in the source. And then we have a function. So this is the first time that we see a function interpreted. This function takes a channel as an argument, and then we'll send a message on this channel. And we have in the main, interpreted main, we have the creation of the channel, and then we have a go routine, which will fork this, not really fork, but which is start this go routine, sending this message, and then we block on print line, and we block on receiving this channel, and print the message at the end. So here, We have, in fact, this is where we are maybe better than other interpreted languages. We are exploiting the full concurrency possibilities offered by the Go runtime within the interpreter itself at no cost, and no, it's exactly the same code as you see in normal compile mode. So just run it. Yeah, it's being, and we could change again. All right. Okay. I said at the beginning that also one of the goals was to be able to create some dynamic code and to make the static compiled code depend from this dynamic code. So let's see now. Let's see. I don't talk about the main first. Let's look at the source which is interpreted here. Select it. Yes, this one. So here, this is a very small package, but it's a fully valid Go package. It's export one bar function, which takes a string as input, and then transform this string slightly. So this is the only code that we want to evaluate. So when now we are back in the application, we create the interpreter, and then we evaluate the source. So once we have done that, in fact, it's exactly if we would have bounded, in fact, loaded and bounded a dynamic library inside the application. It's exactly the same, except that the code that we have loaded is interpreted instead of being compiled. But it's exactly the same as having opened a shared library. And the shared library here is the content of the source. Then we come back to the application, and then what we want to do is to access to the bar function. So evaluate, the eval function just returns a value. And this is why we have chosen to only export one value, because we don't want the people to use eval and directly to test. In fact, to use eval with with the reflect version, but we want them to use eval exactly as they would use a lookup in the dynamic library. We just want them to use eval to access a symbol, and then as soon as possible handle those symbols in compiled mode. So eval returns the bar function. This function is represented as a reflect.value, so we can extract its interface, and then doing a type assertion, we can in fact convert it to a function which is then usable exactly in the same way as any regular code which would have been compiled. So if we run it, okay. So let's look now at the import packages. In fact, the way to insert dependencies. So the first thing that we want to do is to enable the interpreted code to use some binary code. So just run, if I just run it, of course it panics. In fact, I run this wrong example also to show you that we have some level of diagnostic. The import, in fact, this error message here is generated by the interpreter, because we have imported, in fact, in the source, we have imported the package that that doesn't have any source package correspondence, and we have not provided whatsoever yet. We haven't yet provided the binary package, so of course there is an error. So we have this stdlib package. This package is just a wrapper on top of the standard library. So it just, in fact, it just takes any symbol of any exported function from any package of the standard library and wraps it in a reflect.value. This is the only function of the standard lib. So we have imported it, and then we can use it prior to evaluate some code. We can expose the standard library symbols to the interpreter using the use function. And then if I run the code again, okay, so it has printed hello, and it has printed hello with the, this time with the standard library format. Okay, so this is more and more interesting, I hope. So now we can do some fancy things. We can. There was at the presentation this morning a guy say, "Oh, we have this analysis, and what does happen if we analyze the code that I have written to perform analysis?" So, in fact, this is what we want to do here. Of course, we could, in fact, provide the interpreter symbols to itself. So I just import as before the YAEGI interpreter, and now if I look at the, I look directly at the main. We look at the at the source code after. If we look at the main, it's the same story as before. We just create the interpreter. We export some symbols, so now it's not the standard lib symbols that we export, but it's the interpreter symbols themselves, and then we evaluate source. And then if we look at the script, it looks almost exactly as the same as the compiled code, except it's in the script. The only difference is what is provided to eval. Here, in fact, we provide, in fact, instead of evaluating a SRC variable, we're evaluating a hard-coded script. Thank you. But here, if you count correctly, there is, okay, the first level of interpretation there, and then a second level header. Yeah, only second level, but we could continue and add turtles on turtles and on turtles. Yeah, and text, yeah, 42, that's the correct answer. And okay, I left it as an exercise to the reader to make from that program a program which prints itself. I think some people in the Go team are specialists to do this kind of things. So, okay, just now that we have looked at some examples, if we go back, in fact, let's just go back to the interpreter context. The interpreter context holds the states for the Go program, which is running, in fact, which is a kind of sandbox. So it contains the compiled packages as wrappers, and it contains also the interpreted packages. It contains also another thing, which is the frame, which is the memory, which is all the data which is created by the interpreted functions. And the thing is, everything in the interpreter context, in the end, is representing using reflect.value, so it's quite simple. So in local frames and global frames, it just arrays and slices of reflect values, and in compile and in symbol tables, it's just map of reflect values, and the index of maps are just the strings and the name of the symbols. Okay, and now an interesting story, which is at the origin. In fact, what we want to do, in fact, we want to use this kind of interpreter to do something a bit crazy. In fact, to replace some compiled middleware in the HTTP server by interpreted code. So it's kind of crazy. We are in the critical path here. What happens if we slow down some critical functions by interpreting them? So to validate that it works, in fact, we have taken an off-the-shelf package. So there is this JZip handler, which is a package developed by the people in New York Times. And this package just compresses HTTP requests, responses, in fact, from requests. So this is the standard compiled architecture where the JZip handler is fully compiled in the application. And we will compare this version against the same version where the JZip handler is in fact fully interpreted. It's exactly the same JZip handler. We have not changed any line of code. And it works. It works. It's slower. Of course, it's slower. It takes. We have measured in elapsed time. In fact, we have measured maybe 6. In fact, there is between 5 and 10% of overhead. So it's not too bad. I would have expected maybe twice, maybe 5 times slower. And it's not even. It's just a few percent slower. And the main reason is, if I come back there, the main reason is, okay, JZip handler, in fact, it's just a glue code. It's just wrapping itself some logic around JZip. And JZip is the real thing which does the intensive computations. And this JZip package, coming from the standard library, is already compiled and already fast. And so wrapping, using some high-level code in script, and having this script embedded in the application and using just the overhead of converting from reflect values and parsing and interpreting, at the end is quite acceptable, and we can use it really as a plugin engine, and this is what we have performed to, this is what we have chosen to do with this package in traefik. So this is almost the conclusion. I would like to, I have just 2 minutes. I would like to take 2 minutes to do something, something special. So this is, I will show you a kind of secret feature of YAEGI, where we can, in fact, first, of course, we have a command line, but we have also the possibility to display some graphs from this command line. So it's coming there. I sending there, so it's coming. So when I, so here, what we see is the generated AST displayed real time. And so this is the abstract syntax tree, where we see what happens. And now, if I do something, and I have another graph here that I'm sending to the other screen, so it's coming. Yeah, this one is a CFG. It's not an AST. It's a control flow graph. So here we see, in fact, what happens. So it's a bit obscure. It will be less obscure for in the next example. I will do something. I will do just a loop. Sorry. Okay, correct. Yeah. It prints the result, but the interesting thing are the graphs. So let me send the graph on the other side. Okay, so this is the AST graph. So and this graph is generated by the AST package from the standard library itself. Just I've just used the graph wizard package to do the edges and the nodes. So here you recognize, in fact, the code, and this graph has to be interpreted, in fact, from left to right and depth first. And the very last thing, I'm almost off. It's coming. Yeah. So this is what I call the CFG. The CFG stands for control flow graph. So here, the nodes that you are seeing are just the instructions. So if I take the first graph here, let me move it. No, I can't move it. So the instruction, for example, the 21, if I take, okay, let's move it. Doesn't move. Okay. Anyway, in fact, what I wanted to show, in fact, is with this instruction graph, which is the translation of this AST into a kind of intermediate representation, we have, within the this simple line of for loop, we have, in fact, those arrows which are in fact the next instruction. So I do this first one, then I do the test. Then if the test is correct, I do this instruction of print, the block of print. Then the post instruction, which is increment the counter. And if the test fails, then I exit from the loop. And this is, in fact, we have store, we have load, we have a conditional branch, and then we have this strange arrow which is coming up instead of going down, which is a goto. And then here we are just Turing complete. It's just a small definition of a Turing complete language. And this loop, I find it, in fact, I'm doing some computer language history. This loop, in fact, is using the for keyword, which is coming directly back from C. So it's a kind of a legacy legacy language. That in this, I like it very much because it embodies everything which makes, in fact, a programming language complete. In the Turing sense, the initialization, the test, the post processing, and then the block of processing. And finally, in fact, I don't forget that the loop itself was discovered by a woman, which name was Ada, I think, Ada Lovelace, and it was discovered 100 years before Turing wrote this article on the Turing completeness. So I think it's a good way to conclude this presentation. Thank you. And sorry for the glitches, and I was not sorry. So if you have questions.
We already have a question, so.
So first of all, thank you very much for the talk. It was very interesting. And I have a question. So software engineers are known to love writing parsers. So did you, as a part of the project, wrote your own parser for Go, or did you reuse as much from the Go compiler, and why?
Yeah. Okay. So it's open source, of course. So it's, I think if it's, let me go back to there. Yeah. So this is the package. In fact, this is the GitHub project. So yes, it's open source. It's open to contributions. And as I said, in fact, what was your question exactly?
Did you reuse the Go, the parser that is in the Go? Did you reuse the parser that's in the Go compiler, or did you write your own? And why did you make?
Yeah. Okay. We are using the Go standard. In fact, we are using the Go parser provided by the standard library. So this is mainly the AST package. But then, for example, I have not used the SSA parser which generates some code into an intermediate representation which is different from the one I'm using, and mainly because it's not targeted to machine code. It's targeting, in fact, what I do with the AST, I'm compiling closures at the end, so I don't need all the stuff provided by the SSA. And also, I have this is something I wanted to explain, but I gave up. I gave up. In fact, there is a nice property about the AST and the CFG that I wanted to show you before, is that, in fact, I'm using exactly the same data structure to store the AST information and then to store the CFG. The CFG is just using indirections between AST nodes, and this is not something that was easy to achieve with the with the Go tool. So I have a kind of custom package, but I'm still using the standard AST parser. So everything from source to the syntax tree is from the standard library, and then it's custom.
If you go back to the terminal window, you had a loop that went from 0 to less than 4, but then when you ran it, it printed out 4. I was just wondering why.
Yeah, here?
Yeah, that loop prints 4. Why did it print 4?
Good, yeah, maybe a bug. I don't know. Let me... maybe a bug. Yeah, good catch. Sorry. There is probably a bug in the... What happened if I do that? Yeah, I know. Okay, it's not a bug. It's the 4 is the last. In fact, this is the last value of the interpreter. In fact, let me go back to the AST. In fact, this is the last value which is in the 4 node, and it's returned as a value by the interpreter, and then the read-eval print loop print it as a result. So it's a noise. The last 4 is a noise. Right. And because, in fact, Go normally is not supposed to be how do you say? You are not supposed to return values from statements like for or if or things like that. Those are completely void nodes. But for the purpose of the read-eval print loop, I had to propagate the last result back to the AST, and this is the main reason why we see the 4. So yes, this is some noise. This is not a bug in the engine itself, but some noise coming from the REPL. Yeah.
So what happens, like the context of the interpreted part, like let's say you start Go routines there, but then it does return, like back to the scope of your application that is calling the interpreter. What happens to those Go routines? Are they running in the background? Are they actually still there? Or is it like when it returns the exec statement, or what was it?
Yeah.
Is it like gone?
Yeah, okay. Okay, coming back to if I still have I'm coming, where is my cursor? Yeah. I'm looking for this diagram. Yeah, this one. So, after some code has executed in the interpreter, in fact, we still have this interpreter context as a persistent memory in the application. In fact, here I haven't explained that, but if you have started Go routines, this is the only way to. If you start concurrent Go routines, it's the only way to have some forks in the local frames. So if your Go routine that you have started with or without the interpreter is still alive, then the local frame will persist. If the Go routines and if all the Go routines started by the interpreter end up, then you just have at the end of the interpretation the global frame remaining persistent. And then when you quit the function where you have created the interpreter, in fact, all this stuff is garbage collected like any data structure in the Go runtime. So you decide as a user what happens to the.
Okay, so the scope of the code that's being interpreted is the same scope where where the interpreter lives. So if the interpreter is gone, then the code that is okay.
If there is no references anymore to the interpreter, then it disappears as any data structure in Go.
All right, thank you.
Okay, anyone else? No, okay, so thank you very much.
Thank you. Thank you, everybody.